Hello, I'm Tom Blue. I'm a student at Lancaster University and I'm a researcher there as well. I'm going to be talking about assembly and software reverse engineering. So, who am I? What are my credentials? This is a WannaCry. It was a long ransomware attack in May 2017. It affected many organizations like the NHS, FedEx, and big important things. We're going to be approaching this talk from the perspective that we're trying to use software reverse engineering to find out how to stop WannaCry. So where do we begin? We begin with assembly. Assembly is, it consists of simple instructions that work on a number of fixed-size variables known as registers. Registers are stored within the CPU and can be accessed very quickly. Anything that doesn't fit in a register goes into memory, which takes longer to access, and it runs line by line. So, about memory. Memory is broken up into various segments. There's the text segment, which holds the code within the program, and that's the only real executable part of the part of memory. The stack used to be executable, but that was a major issue because you'd be able to insert code into the stack and then execute it. So the stack was made non-executable. Data segment holds variables. Read-only data is literals and constants. Read-only data can't be modified, as the name implies. The heap contains dynamically allocated variables, so anything that's allocated when you use malloc. And stack contains stack variables, and it consists of stack frames. How does the computer know what line we're on? You didn't ask, but I'm going to answer regardless. There's a number of special purpose registers. These contain values which are important to the program's execution. Some examples include the instruction pointer, which points at the current line we're executing. The instruction pointer is incremented after each instruction is executed and is modified by instructions such as jump, return, etc. There's the base and the stack pointer. I'll go into stack frames in a moment, but the base pointer points at the base of the stack. The stack pointer points at the top of the stack for the current stack frame. And stack frames are generated when a function is called and destroyed when the function finishes. The stack frame holds the variables for that function whilst it's being executed, which is why you can't access a function, a variable that's declared in a different scope. Oops. There's the flags register, which holds a number of important flags, such as the 0 flag, which is set when the previous operation equals 0. That happens when, for example, if you subtract one thing from another and they're equal, the result will be 0. So it's important for stuff like that. There's the overflow flag, which is set when you add two numbers and the number is greater than the value that can be held in that register, in that it overflows. So, going on to stack frames. When the call instruction is executed, it pushes the instruction pointer and the base pointer onto the stack, and it sets the base pointer to be the new stack pointer. The base pointer becomes the current stack pointer. So effectively, the start of the new stack is where the old stack ended. And then the address of the instruction pointer is set to the address of the function you're calling. When you return, you pop the instruction pointer and the base pointer back into their respective registers. By the end of the function, the stack pointer should be back to where it was before anyways, because all the local variables used within the function will have should have been popped off the stack by this point. Then the instruction pointer is returned back to what it was before, so it can continue execution from where the function was initially called. And the base pointer is set back to the base of the previous stack frame. So, how does this all relate to WannaCry? I didn't know what image to put here, so so compiled code can be converted to assembly. We could try and figure out how the encryption happens and if we can undo it. we could look at how it spreads and try to prevent it. We could try and write an antivirus signature for it. Or we could hope that the malware authors put a convenient kill switch that we could trigger. So about reverse engineering, there was supposed to be a slide here, and I did the exact same thing in Cambridge when I initially gave this talk, about like what is reverse engineering, but I've clearly forgot to add it again, so I guess we're going straight to dynamic analysis. Dynamic analysis is where you actually run lines of assembly. This is useful because you get to run the assembly line by line, you get to run chunks of assembly and see what the output is and see what happens with the registers, and that way you can kind of quickly deduce what the function is doing without having to manually go through each line and work out what each line of assembly does. You can set breakpoints and see register values mid-execution, which is really useful for trying to figure out what the program is doing. You could look at memory areas such as the heap and the stack, which is again useful because if you look at the variables on the heap and stack, you can kind of and see how they change throughout the execution. You can figure out what the program is doing and hence figure out how it's vulnerable or how you could modify it the way you want. The only downside is that if you're running malware on your computer, you might accidentally run the malware, which could be problematic. So, other than dynamic analysis, we have static analysis. Static analysis is where you look at each line of assembly and just kind of figure out what it does without actually running it. There are tons of really useful tools for this, like ghidra, which I'm going to show in the live demo at the end. You can view functions, symbols, etc. Most tools will allow you to automatically analyze a lot of things, and it will figure out kind of a little bit of what's going on by itself. Some tools like ghidra have decompilation output, so you can kind of look at what the compiled C code would be like. Speaking of which, one thing I was going to do was so there's this really useful site called Godbolt where you can write code in a language and it will compile it to assembly, and it's useful to kind of see what your code looks like in assembly, because when you see similar patterns in assembly, you can then kind of recognize, oh, this is a for loop, or this is an integer, or whatever. So we'll write a basic, some basic C code and see what it compiles to. So what happened is, in the beginning you can see it pushes the base pointer and sets the stack pointer to be the base pointer. That's what happened at the start of each function, as mentioned before when you run call. It then sets a couple labels. So it moves parameters into various registers before calling printf. Those are the parameters which we give to printf. So in this case, I, the variable within the for loop. It will then compare I to 4 in this case, because I compare I goes up to 4 before the loop finishes. If it's less than 4, it jumps back to the previous label and repeats until eventually it doesn't, and then it returns at the end. If anyone has any suggestions for C code to write to see what it looks like in assembly, then
ChatGPT to write. It's recurring. Calculate pi to 10 million codes.
That would probably generate a lot of assembly.
ChatGPT to do that.
Fair enough. You can ask ChatGPT what the last number of pi is.
Yes.
So going back to the presentation, so viewing functions, decompilation. There's cool control flow graphs where you can kind of like have arrows that point to where things are going, which is helpful in visualizing what's going on in the code. Like if you see arrows that point to themselves, you can kind of recognize that's probably a loop of some sort. You can kind of see where key decision points are, which is useful when you're trying to figure out what certain code is trying to do. And there's no risk of accidentally running malware on your own system, which is nice. It's a bit less than ideal if you accidentally encrypt your virtual machine, or hopefully not your actual. So why is this useful? We get to work out what the software is doing. We get to modify application behavior, which is called patching, and we'll get onto that. And we can find otherwise difficult to spot vulnerabilities because you're kind of methodically going through the actual assembly. You don't necessarily need the source code. You can kind of find vulnerabilities through the code itself. So, patching. This is where you go through a binary and you change instructions to change how the program behaves. So you can directly modify the code without having access to the source. This can be used for things like skipping authentication checks. If you find like a jump less than and change that to like a jump greater than, for example, then you're effectively reversing how the program functions. If you can find places whilst reverse engineering that you can modify to significantly change how the program behaves, then you can kind of get the program to behave however you want it to. This is how a lot of cracking software works. And yeah, you can literally just change what the code does. Padding can be a pain though, because the CPU the compiler will pad the assembly to a certain number of bytes, and the CPU reads it in at that number of bytes because that's more efficient for it to, rather than check how long each instruction is, reading the same number of bytes each time and ignore any padding. But then when you begin directly modifying assembly, if the padding gets screwed up, it's just a massive pain. So, buffer overflows. This is a prerequisite to return-oriented programming, which, to be honest, I've just added because I find it really cool. So, a buffer overflow is where if you've got, for example, a stack variable with a specific number of bytes, what happens if you read more than that number of bytes? If you have a 5-byte buffer and you read 10 bytes of information, what happens is you'll fill up the 5 bytes within that variable, but you'll also overwrite the 5 bytes after the variable. So other variables which are on the stack you can modify by effectively filling up the variable you're actually modifying and then modifying whatever comes after that too, which can be very useful in a lot of cases. One of those cases is return-oriented programming. So going back to how stack frames work, when you return from a function, like I said, it pops the instruction pointer and the base pointer off of the stack back into their respective registers. So return-oriented programming is super cool. Like I said, return pops a value from the stack into the instruction pointer. You can use what are effectively, or what are called gadgets within ROP. These are a couple lines of assembly which end with a return. If you have a buffer overflow in a program, you can overwrite the return pointer on the stack. That means that rather than return to wherever the function was called from, the function will then instead return to wherever you want within memory. Going back to how the data segment is the only bit of memory which is executable. In the past, what you would do instead is put shellcode onto the stack and change the instruction pointer to point to your own shellcode on the stack and execute that. You can't do that anymore because the stack is non-executable. The CPU will refuse to execute code on the stack. Instead, what you do is you find a couple lines of assembly within like the standard library or somewhere in the data segment that you want to use, which end with a return. And then when that return executes, whatever value is on the stack after that, which you've also modified, it will return to that. And you can effectively string them together to get arbitrary code execution without actually having to write any code. And this gets around the whole non-executable stack because you're not executing stuff from the stack, you're executing stuff from the data segment, which is the only executable part of memory. So it's effectively arbitrary code execution. Live demo time. When I did this talk in Cambridge, the live demo gods had mercy on me. I'm going to hope the same holds true here. So, as hinted at before, this is a copy of WannaCry, which I've got open in ghidra. Yeah, as I said before, WannaCry, if you're not aware, WannaCry had a kill switch, which is just a domain within the code which, when registered, will stop WannaCry from being able to affect things. I had the idea of, I could structure the talk as kind of a story about WannaCry and then have it end with stopping WannaCry. That would be really cool. And I found a sample of WannaCry online, and I thought, I'm just going to reverse engineer this as I would anything else and find the kill switch myself, because I knew it wasn't very difficult to do and I'd done it in the past. What I didn't realize was the sample of WannaCry I downloaded didn't have the kill switch in it. So I spent about 4 hours whilst preparing this talk reverse engineering WannaCry, trying to find the kill switch, which I knew was somewhere obvious, and being unable to because it didn't exist. And I only came up with the idea of running strings about 4 hours in, and I realized there was no kill switch. And yeah. So with ghidra, ghidra has a lot of options to auto-analyze whatever code you're looking at. So when you first open up a file in ghidra, it will spend a little time automatically analyzing everything, and it'll come up with this decompilation output where it takes the assembly, which you can see over here, and turns it back into kind of a C-like pseudocode, which the decompilation output can be inaccurate at times, but is a useful tool which you can modify yourself as you begin to make it more accurate, to kind of keep track of what the code does and over time build up a better picture of how something works. So pretty much every program starts with the entry function. The entry function is the exact same code every time. And the important thing we're looking for is where it calls, in this case, since this is a Windows program, the win main. Because there's been some obfuscation, because malware obviously, symbols have been removed and ghidra can't detect where win main is, but it can always detect where entry is. So you can look at entry and find where win main probably is, which should be this. And if you if you click on it, it should jump to this function. So we know that this is win main. Like I said, you can modify the decompilation output in ghidra to make it more accurate as you learn more information about whatever it is you're reverse engineering. So in this case, we know this is WinMain. We can look up the Windows documentation and find the function signature for WinMain. We can then go into ghidra, and we can modify the function signature and effectively just copy and paste the signature from Windows. So this means that ghidra will go back and will reinterpret all the variables which are in. Like at the moment, WinMain takes quite a lot of parameters. ghidra doesn't know what to do with those parameters, so they aren't included in the decompilation output. When you include those parameters as you redefine the function signatures, ghidra can then go back and look at the things that were passed in and recognize, oh, this is a thing which is being passed into this function. So, okay, so we've modified the function signature. It now recognizes what each parameter that was passed in is. The decompilation output often starts with a bunch of variables in the beginning, which are given various undefined data types. Undefined 4, undefined 2, etc. is just like undefined 4 is just an undefined 4-byte variable of some sort, and when you go through and you're able to identify what that might be, you're able to redefine it within ghidra, and it will be able to go back and work out what each thing is. So, for example, we have puvar3, which is being set to a pointer, a 4-byte pointer of some kind of string. We can infer that this is a character pointer. So we can go to puvar3. We can retype the variable to be a character pointer, and now rather than cast this string into a undefined 4-byte pointer to pass into the undefined 4-byte pointer, it now knows that's it's a pointer to a character, and it's now pointing to a character, to a string of characters. puvar4 is a pointer to puvar3. So then we can also infer that this is also a character pointer. So we can retype this too. And so as you go through, you're able to kind of take these undefined data types and work out what they are. And as you do so, ghidra will also go back and figure out what it is the function is doing within the information you give it. This is incredibly useful because it means you don't have to go through as much assembly, which can be often a little overwhelming. And you can instead build up effectively a pseudocode of what the program is doing, which is much easier to analyze and much easier to kind of find vulnerabilities with. So looking at the WinMain, we have this function puvar3, and then puvar4, which we know is a character pointer, is being set to local 50, which is being cast to a character pointer. So we can find local 50. Local 50 is an array of 4 undefined, an array of some data type, which is an undefined 4 bytes. We can infer from this the fact that it's being that is being assigned to a character pointer, that the undefined 4-byte data type is also a character. So now PUVAR4 is being set to the reference of PUVAR of local 50. Effectively, it's pointing to the address of local 50. ghidra has correctly identified that there's a for loop here. And what the for loop is doing is it's copying PUVAR3 into PUVAR4 and then incrementing it. Since PUVAR4 points to local 50, it begins to point at the beginning of local 50. As you add 4 bytes to it, it moves along. And each item within the array is populated. And then eventually eventually it runs some functions to run a URL on the internet and goes into another function. We can go into the next function and see what's going on. Over here, ghidra has been able to identify some of the functions which some of the data types of the variables. However, we do kind of have to take this with a grain of salt. With the win main, the decompilation was slightly more usable because we knew the function signature. Over here, we don't necessarily know if this is a void function or if ghidra was simply unable to identify due to obfuscation or whatever the parameters of the function that it's looking at, which can lead to weird issues with decompilation. And at this point, you'd have to go into the assembly and try to figure out manually what's going on and see what's being passed into the function. So if we go back, we can see the function call for whatever function this is. Generally, if there's parameters being passed, those are moved into local registers, which will then hold the parameters through the execution of the next function, or eventually be pushed into the stack. As there are no such as there's no value being moved into registers before the call, we can be somewhat certain that there are no parameters within this function, which means we can trust it a little more. Again, we don't know whether it's void either. But yeah, and that's something else you'd also have to kind of try to work out as you look through the assembly. So anyways, with WannaCry, like I said, it was in a very obvious place, and to be honest, one issue with this kind of demo of sorts, but it's kind of obvious where the kill switch is, because the first thing you see when you open WinMain is the URL. And in the actual WannaCry attack, when I think it was Marcus who tried to reverse engineer WannaCry, found the kill switch. He initially registered it as a domain to try to track infections, not realizing what it actually did, but it turned out it stopped WannaCry entirely, until eventually they created a version without the kill switch. But, yeah. So anyways, I feel like that was a lot quicker than it was supposed to be, but that is the end. When I entered end into PowerPoint, one of the design suggestions was this. All it added was a line, and I found that quite funny, so I thought I'd keep it. If you have any questions, then...
Yes.
Yeah?
Towards, when you went for the second function there, it said, how much do you need to understand to reverse that function? Is that at that point it becomes a bit more guesswork?
I'd say at that point, I wouldn't call it guesswork. It's just more. I suppose it's less automated. It's more manual in terms of. It's just more looking through the assembly and figuring out what it does. I wouldn't say like it can often, depending on what you're looking at, it can often be more tedious than it is difficult, if that makes sense.
So, yeah, because in my head, on the side, that it could have sense or not.
Yeah. The reason I kind of included the whole, this is what certain C code looks like in assembly was because one exercise which I found very useful and I did quite often was writing my own programs and then trying to reverse engineer them, because then I'd be able to go through and say, oh, this is where I wrote that for loop, or this is where that if statement was, or this while loop was, and you can kind of identify, oh, this is what a while loop looks like in assembly, or this is what this or that looks like in assembly. And then when you're going through like an unknown function and you see those same patterns, it's like you can kind of recognize, oh, this is probably a while loop or a for loop of some sort, because you've seen that pattern before. Are there any more questions? Yeah? So sorry, I couldn't quite hear what you said. How did he extract? Well, the assembly code is just when code is compiled, it gets turned into machine code, and that's what's executed on the CPU. That machine code has a one-to-one correlation to assembly, so you can effectively just convert that machine code into perfect assembly and look at it that way. That's why looking at assembly is useful, because like you can not share the source code, but you can't not share the assembly, because if you don't share the assembly, then you can't share the program. So if you have the program running on your computer, you can get the assembly and look at it, regardless of what that program is. Any other? Yeah?
So thank you. Take a really cool topic and made it very interesting. Most people in security won't be doing binary analysis or building assembly. What kind of roles and jobs is this used for in cybersecurity?
So I would say it's probably at the university, for example, I'm a researcher, and some of the stuff I do is on embedded systems, and a lot of that is looking at assembly because you often just can't run high-level code on a machine with such restraints in terms of memory capacity and kind of compute, and then to kind of do anything, you have to understand the assembly and look at it that way. In malware analysis, it's essential to be able to look at compiled programs and see what they do. I mean, it is quite a niche topic, but it's also quite an important topic because stuff like malware analysis is important. If you were writing antivirus signatures, for example, it's useful to be able to go through malware and see and kind of see patterns that you could write into a signature. And yeah, like I mentioned before, cracking programs, modifying them, stuff like that too is useful too. Yeah?
Yeah, so SOC analysts, that kind of work.
Yeah.
Heavily involved in SWI and IPS signatures and stuff. It's really, really imperative that you understand what you're looking at to be able to write at least a signature prevention. So if you've got, I did quite a lot of this years ago when I was at the transport police because we didn't have an IPS, so I just used Snort, wrote a lot of sort of pre-processing signatures in that. So it's useful for that, and my knowledge of assembly is zero. It would have greatly helped if I paid attention when I should be learning that, rather than trying to reverse my way through it.
Yeah.
How does it work with dynamic libraries?
With dynamic libraries?
Because I can understand if you've got everything all in one big binary block, you've got everything. Actually, if you've got things going outside the program, how do you see the interactions?
The answer to that is kind of, you don't really need to. In that, so when you look at a program, there is a lot of assembly, and you kind of have to learn what you need to ignore and what you need to actually look at. stuff like standard libraries, including dynamic libraries. The code often isn't very interesting. Once you figure out what function is being run, that's kind of all you need to know, because you can find everything else you need out from the documentation. When you're reversing a program, the thing you're looking out for is effectively the stuff that the malware author or the programmer wrote. So, like, their own logic of how they use those functions, rather than what those functions specifically do. If you were to reverse engineer the entire standard library, you'd never get to the actual...
Just thinking if you modify something that's so common, then you'd actually have a greater attack surface than just one application.
Yeah, that is true. I suppose in that sense, you'd be more reversing...
Take print, for example. Yeah.
Yeah. In that case, that would be less reverse engineering a specific malware or software, and more reverse engineering that library. I don't think you would reverse engineer that library as a part of looking at malware, but you could absolutely do that separately as its own thing, and people absolutely do it.
I'm just being annoying. It's time to have to be annoying. And, if you did that, something like that affected things in such a random way,
yes,
then that takes the availability out of the system and suddenly wastes people's time.
Yes.
And actually, that's what an attacker wants to do, is waste time.
Yeah.
So, yeah.
Are there any other questions?
Doesn't look like it. Thank you again, Tom.